All right, so this is the first lecture of microprocessor. Just right after you are done with C++ review, you can start working on this one because you'll have a quiz for each and every lecture, maybe one or more. So, addressing mode. We don't know anything about the addressing mode, but before we start anything about this, what actually the microprocessor? Remember, the microprocessor is not about only the computer. These days, in every single digital device, you have a microprocessor. Matter is a computer, it might be a cell phone, it might be any iPad, notebook, even the printer, even like a refrigerator, even you have a vending machine. You have some sort of microprocessor there. It may not be as powerful as like your laptop, as powerful as like your desktop, but there is something, okay? But in this class, our attention is not about the speed. We will not be talking about the fastest microprocessor of the world like we have right now in front of us, but instead we'll be trying to understand how the microprocessor works, meaning how actually the microprocessor uses instruction, okay, to execute things, meaning how your instruction that you give to the computer that basically is executed, meaning is understood and executed by the microprocessor. That's the main purpose of this class, okay? Even if we are, because in the lab we will be using a family of microprocessor which is basically designed by Motorola, because that is open to educators, meaning, you know, as a student, you, and as an instructor, myself, we can access to their set of instructions. We have access to those so that's why we'll be using the Motorola microprocessor instead of Intel, because, you know, all the machine you have in front of you, most of the microprocessors are from Intel, and sometimes you might have seen some processors in your laptop or at home from AMD, right? Have you heard about the AMD? That's another microprocessor, right? Surprisingly, even if AMD doesn't look like that they are the pioneer in computers, but pioneer in microprocessing, but they are the first company who basically invented microprocessor. You probably have never heard this from anybody. And at that time, it was not even called microprocessor. It was called advanced micro device. And that's how AMD came into the, you know. So basically, the AMD is the first company who basically invented microprocessor, not the Intel. Intel is the last one in the business, who was the fourth, because there were several other like Motorola and IBM. They also had the microprocessor, they are not in the business right now, probably just like the Intel, but they were also some part of it. I'm saying they also deserve some credit of this. Now, again, the microprocessor you have, meaning the machine you have in front of you, most of these machines can handle 64-bit data, right? Because remember, when you buy the computer, what it said, oh, 64-bit machine, right? Those are some business words, but, you know, still they have some meanings also. I'm saying they have some technical meanings. Whenever you see 64-bit machine or 64-bit operating system, right? These days, most of the things are 64-bit, and I'm sure that over the time, within a couple of years, you will see everything is 128-bit, because, you know, it will be always like that, because it's also a part of business and part of, you know, people get rid of their old machines and new machines and speed also. So, surprisingly, in this class, we'll talk about not like 64-bit machines. We'll talk about an 8-bit microprocessor, okay, which is a Motorola microprocessor in the lab, and all the instructions, all the discussions we'll have in the class will be based on that microprocessor. But the idea is not to understand how the Motorola microprocessor works. Idea is to understand how the microprocessor works, but we have to use one as an example. That's why we'll be using the Motorola as an example, but the intention is not to understand the Motorola microprocessor. Intention is to understand any microprocessor of the world, and over the time you'll see that if you understand how this microprocessor works, how the set of instructions we have, we understand it, we'll be able to use any microprocessor, any set of instructions. At this point, it's probably not too clear, but over the time it will be more clear, and I'll get back to this point again, okay? But again, microprocessor is actually a digital circuit. It's an integrated digital circuit, because if you really try to build a microprocessor using your breadboard, this room may not be enough. That many circuits and connections will be there, but it's integrated, and we are blessed with the VLSI technique, large scale integration, and they can compact the circuit like that compact, but that's a huge big circuit which is integrated in a very small chip. Okay, even if that is a small like 4-bit or 8-bit microprocessor, you still have a lot of circuit there. Okay, again microprocessor like a 4-bit microprocessor. What exactly means by 4-bit? The 4-bit means that it can handle 4-bit data. Now what exactly meaning by handle? You probably heard it before but never have tested. The microprocessor, no matter which one, no matter even the one that you have in front of you, the only arithmetic operation the microprocessor can do is addition, nothing else. It might be funny that the whole world is running on microprocessor these days, because no matter what you do, I'm saying computer, cell phone, iPad, iPhone, no matter what you are doing, you are basically executing some instructions just by clicking or tapping or whatever. But your microprocessor can do only one operation, arithmetic, that is addition. Even when, remember the digital circuit class, and also here I gave you a couple of example pages. Remember this was like an example of subtraction, right? The binary subtraction. But you have realized that in the binary there is a technique of subtraction, but instead of just learning that technique, I emphasized in the class to understand how we do the subtraction using 2's complement method. This is called 2's complement. Okay? If you really look into this method, you will realize that we have never done any subtraction, because at the end we actually do an addition. But eventually that is basically having a subtraction, because we just want to know these, because this is exactly how the computer does the subtraction. Because it does the subtraction using a way of addition, because it doesn't know how to do the subtraction. And technically, if you know the addition, you can do the subtraction, and if you know the addition, you can also do the multiplication. If you know how to do the subtraction this way, you can also use this subtraction as a division. So that means microprocessor just knows one arithmetic operation, which is addition, but it does it so fast that you don't realize that it doesn't know anything else. Meaning, I'm saying in 1 second, it basically is doing probably million additions. You see what I'm saying? So all the operations are basically can be defined in terms of addition. Since you can do subtraction with addition, you can also do multiplication with addition, you can also do division with the addition. Okay? So pretty much you can cover all the the technical operation, like all the mathematical operation, just by one single addition. But it can also do some logical operations, like comparing two numbers, which one is bigger, and I'm saying which one is greater, lesser, okay, those kind of things. But again, not too much. But these days, you see, you click it, it does like so many things in 1 second. The only point where it basically beat everybody is speed. It can do only addition, but it can do 1 million addition in 1 second. Nobody can do it. Like I'm saying, no human being can basically beat that. So that's the point where basically microprocessor is so faster, and microprocessor is doing so many things, because no matter even if you are like your GPS or like tapping something in the cell phone, in terms of the whole operation is just one addition. I'm saying millions of addition. Okay, so technically it just knows how to do the addition. So that means what? If you have a 4-bit microprocessor, it basically can add 2 4-bit numbers, meaning 2 4-bit binary numbers. If it is an 8-bit machine, it can add 2 8-bit binary numbers. Now in front of you is all 64-bit machines. That means these machines can add 2 64-bit number at once. Now you might be wondering what happens to the 8-bit computer, meaning the microprocessor, when you have a 64-bit number addition. It can still do it, but it has to do in multiple steps. 8-bit at once, next 8-bit, next 8-bit. You can you can do the 64-bit addition in 8 times, but you have to propagate the carry. I'm saying you can always do that, but it will take a little bit longer step, like 8 times slower than, not 8 times slower, it will be much slower, but at least it will have 8 times more steps than the one that you have. So it's, whenever you have more beats, you can handle more data, faster, little bit. So that's why people are running after those, and designers are running after those. All the computer engineers, architecture, meaning all the people who basically like in the Intel, who build the motherboards, meaning the main boards of the computer, they are running after all the new architectures. And again, In this class, we'll not be running after that, but we'll try to understand how exactly it works. And to understand that, we'll take a very simple example of microprocessor, which is an 8-bit microprocessor, and which is enough for us, because over the time you'll see how that exactly will help you to understand how the 64-bit microprocessor also works. Okay, and again, the family of the microprocessor that we'll cover, because that is a family of the microprocessor from the Motorola. The name of the family, that is a name or series given by the Motorola, is called M6800. That's the family of the microprocessor, and we'll just use one of the microprocessor from that family. Okay, so that's why our microprocessor, the series number of the microprocessor will start by M6800, and there will be some more numbers after that. Okay, again, this is probably a very basic architecture of the computer. It looks so simple, but technically simple, but it still takes something to understand. So what actually the microprocessor does? Look at this. You have some sort of input and output port, right? For an example, how you are giving the input? Keyboard, mouse, scanner. There are probably some others, right? Output, monitor, maybe projector, maybe printer, right? Several other ones, right? So technically, what actually the computer does? You basically are giving some input, you are telling to do something, and microprocessor at the end will return something as an output, right? That's all it does. And to do this, it also requires some sort of memory, right? Remember, anytime in this class I refer memory, that means RAM, not hard drive. It's RAM. You know the RAM, right? It's random access memory. So we're talking about the memory. So now, and also they have some sort of connections, right, among them. So because you are basically communicating with the microprocessor is trying to load some data from memory, from you, from different places. And we have some buses here. Buses, some sort of connections, okay, between communication channels. And they have also some sort of address bus, which basically microprocessor use to locate the locations in the memory. Because you see, the memory is like whenever you have a, let's say, an 8 gigabyte memory, right? These days, all the machines are like what, 8 or 4 is very less, right? 8 or 16, even 32 gigabyte. Now, think about the 8 gigabyte memory. Every single memory location is just 1 byte, right? How many memory locations do you have in 8 gigabyte? It's huge, right? I'm saying because one location is just 1 byte. But that's still like 8-bit. We understand the bit and byte, right? 8-bit makes 1 byte, meaning 8-bit binary number, because it's all binary. Now, how many bytes you have? It's plenty of bytes. Now the question is, how you are going to locate the 1 byte there? Because that means what? Every byte needs an address, right? Think about this. Every single byte needs an address. And you have so many bytes, even in 8 byte, it's a huge, right? That means your microprocessor basically use some sort of addressing to locate different locations out of this 8 gigabyte or 16 gigabyte or whatever, 32 gigabyte, okay? You have even seen that when we had 32-bit machine just before this one, now we have 64, right? You cannot use even more than 3.33 gigabyte of RAM. Why is that? Because using 32-bit, you cannot generate that many addresses. Okay, now let me make it a little bit simple. Okay, now, can you tell me, let's say I give you 4 binary bits, okay? Just using 4-bit, how many number you can write? Binary, using 4-bit, what you can write? You can start from 0, right? How far you can go? 15. 1, 1, 1, 1. That means what? Just using 4-bit, you can write only 16 numbers, meaning 0 to 15, right? So you have restrictions, right? You see something? Okay, how about 8-bit? If I give you 8-bit, how many numbers you can write? 256, because the largest number you can write is what? All ones, right? 1, 1, 1, 1, 1, 1, 1, 1, meaning 8 ones. That is what? 255. in decimal, right? I'm saying you can convert it. You know how to convert between decimal and hex, right? I'm saying decimal, binary, and all of this. So that means what? Just using 8-bit, you can write 256, 255. That is the largest number. I'm talking about the unsigned. Don't get confused by the sign. So the unsigned number. So that means what? In total, you can write only 256 number because it's 0 to 255. So that means you see there is a restriction. Every single, but whenever I am just, I'm just making the length longer, you can write more numbers, right? How do I know how many numbers I can write? Any guess? When you have 4-bit, you can write 16 numbers, right? It's very simple. Just use 2 to the power 4. When you have 8-bit, you can write 2 to the power 8, which is 256. When you have 4-bit, you can only write 16 numbers, right? 0 to 15. That means if somebody asks you, I give you 4-bit, how many numbers you can write? You can just directly tell from 2 to the power 4. Just do 2 to the power, okay? Now using 8-bit, you can write 2 to the power 8 numbers. 2 to the power 8 means what? 256. Yeah. So using 32-bit, you can write what? How many numbers? 2 to the power 32. But think about 64-bit. It's 2 to the power 63. It's a huge higher number than 2 to the power 32, right? And that's why everybody is running after the new architecture 64-bit where you can have more memory locations because every location needs an address and address is a number. If I just give you 4-bit, let's say I said, okay, can I have a computer microprocessor with only 4-bit microprocessor? Then your memory locations will have only 16 locations because every location needs an address, right? Address is a unique number because you just have 16 numbers. You cannot write anything more than 16. Do you see the problem? Now, when you have 8-bit numbers, you can go at max what? 18-bit? I'm saying 256 numbers. So you cannot have even one gigabyte of memory, right? That's the point. That's why people are running after 64-bit now, because they have more memory locations. They can point more locations because older days, not even older days, it's probably even 2 years back, we used to have like all machines in 32-bit, right? Even 2-3 years back. So even I think 4 years back it's almost like all 32-bit because we cannot even have memory more than even 3.33 gigabyte because it cannot locate that many locations. You cannot have that many addresses, okay? But over the time we'll understand this more. I was just a little bit focusing on some of these so that you can get motivated and see the point of having such a class, okay? And now you have some applications. I'm sure that this is not enough. I tried to write something from the text so that you can see some connection from the text, but I'm sure that we have much more applications of microprocessor right now, and I don't have to probably enhance or explain much because we can see microprocessor everywhere, okay? Okay, now this is a little bit of something that might give you a little bit of idea that how actually the microprocessor works. Remember, you probably will not understand every single detail here, but I'm just trying to give you a little bit of idea that how actually the microprocessor works. Now for an example, let's say this is your microprocessor, okay? This 6800 is your microprocessor, okay? Now here, this is your memory locations, meaning this is your RAM. Now remember, in the RAM, we are trying to give you every byte. Now this is the first byte at the top, right? This is the first byte. Now then this is the second byte, that's the third byte. Now every byte has an address, right? Every byte needs an address, unique address. I would say every byte needs an unique address because if it is not unique, let's say if my house address is same like your house address, that doesn't make any sense, right? It's just like the house address because every house in Memphis City or in Shelby County, we have a different address, right? And similarly, every location has to have a different address, and address is just a number, okay? That means what? The address of the first memory byte is, let's say, 0. Address of the second byte is 1. Next byte, 2, let's say, okay? Now let's say these are the connection between the microprocessor and the memory, meaning using this connection, it basically transfers the data because sometimes microprocessor loads the data. Loading means it basically takes the data from the memory and load it to the microprocessor, okay? Sometimes it stores the data. That means from the microprocessor, it basically put it back to the memory. Okay? But you don't know which memory, right? Now you see here, there are 16 lines in this side. Do you see? This, I'm talking about these lines. Do you see the 16 lines here? You can count. These are 16 lines. That means these are actually used for the addressing. Now tell me what number you have here. Can you read? 0, 0, 0 all the way to 1, 1. What is this number? It's 3, right? Binary, 1, 1. It's 3, right? Now by this, which address location you are talking about? This location, right? You see what I'm saying? So that means just by changing that address bus, you are basically pointing one single byte of the memory locations out of all. At this point, this is just 3, right? 0, 0, 0 all the way to 1, 1. Okay? Now, so you will pinpoint which address it is. Now, look at this another line here. There is a single line here which is used as a read-write line. Do you see it? This line? Now, just by reading this one, what do you understand? Read/write bar. What does it mean? Just as a guess. I'm not saying you should know it. I'm just asking, can you guess? Now, that means what? If this line is 1, microprocessor is in reading mode. If it is 0, it is in writing mode. Now, what is reading and what is writing? Now, reading means data will be transferred from memory to processor, right? Because it reads the data, meaning whatever you have in memory, I'll read it. Writing means microprocessor to memory, okay? So you can always change it. Now, let's say I have a data here, which is what? Let's say I have a data which is 0011 0100. This is the data, 1 byte data, okay? Yes, because reading is R, right? And W has a bar. Anything has a bar, that means there's 0. Yeah. Meaning that is activated when the input is 0. Okay. Now, let's say we have a data here, 0011 0100. That's a data, right? Now, let's say microprocessor is what? Reading mode or writing mode? Reading mode, right? You see, that line is 1. Microprocessor is reading mode. Now, can you tell me from which byte it's reading? From which location? It's from memory location 3, right? Because in the address bar, I'm saying that in the address bus, you have 3, right? Now check the data you have in 3. What do you have in 3? Check the data you have in 3. What is the data? 0011 0100. That's exactly the same data here, right? That means that is the data is just read by the microprocessor from the memory. So this is an idea, very basic idea, how things work. But now, the next question might be, who is controlling this data? Meaning, how you get this data, or how we have 1, 1 in the address bar, or how microprocessor is set for reading or not for writing. How is that? Just because it's basically you who is controlling it, just by writing the instruction. Why did you write it? In the programming language. When you write the instruction, microprocessor takes the instruction and execute it, right? You just read what you are writing. So in this class, you will be able to write directly for the microprocessor, which is directly readable by the microprocessor. But the problem is in the high-level language like C++, in Java and C# or scripting language, you don't write directly for the microprocessor. You write which you understand better, and compiler basically translate that, like in 1 line, translate it to like 20 lines, so that microprocessor read each line and do it. Okay? Because in high-level language, what do you do? You said, okay, can you tell me what is the string length of this variable? Think about the microprocessor. Does the microprocessor understand what is the string length? Microprocessor can only do addition and subtraction, right? Addition, right? So it basically decoded by the compiler so that, oh, do this, load this, add this, subtract this, you know, those sort of things. So we'll understand this in this class. You see, we are not trying to understand all sort of details of these at this point, but I'm trying to show you some bigger picture, okay? But at some point, at the end of this class, we'll have much better understanding of how things are working, okay? But this is a very basic. Again, just to start with, we have some, remember, have you heard about the cache memory? I'm sure you have, right? When you buy a computer, A lot of times you have seen that they mention the microprocessor has a cache memory 3 megabyte. Still in these days, cache memories are like 3 megabyte or 6 megabyte is probably 8 megabyte is probably highest I have ever seen. Even in these days, you might be wondering why it is so low. I'm saying 8 megabyte is, we are talking about like 8 gigabyte in RAM or 16 gigabyte or 32 gigabyte, because the cache memories are extremely expensive, and those are basically with the microprocessor, okay, inside the microprocessor. Or those are actually the fastest memories we have in the world. It's even much faster than RAM. Now, that means what? Microprocessor has some own memory locations. Those are not RAM. Meaning, in those locations, actually microprocessor does the addition. As I said, microprocessor can do addition, right? So it does the addition in those locations. It basically pulls the data from the memory and it does the addition in those locations, okay? CACHE, cache. But again, remember, in this class we're not talking about the cache, but we'll be a little bit more specific. These are called registers. These memory locations. So the specific microprocessor we'll be talking about, remember I said we have a microprocessor from the 6800 family, okay? We have some registers, okay? And we just need to see those registers, need to work with those registers, and we'll be exploring with this set of register for this semester and also for in the next semester as well, okay? In the next class of microprocessor, which will be a microcontroller class. Now, we have a list of registers here. You see these registers have some name. This is the accumulator A, this is accumulator B, and these are 1 byte each. Do you see? These are 1 byte. And some registers are index register, 2 byte, stack pointer, 2 byte, program counter, 2 byte. This is condition code register, this is 1 byte. Now remember, at this point, just know the names. Over the time, we'll see their purpose, we'll understand more better that why these are introduced, how these work, okay? Just know the names at this point. So every microprocessor, let's say for the microprocessor we are talking about, we have some specific registers. In this register, microprocessor basically does the operation like the addition or the comparison, okay? These registers, these are some memory locations, but these are not located in the memory. These are located inside the microprocessor, okay? Now, we are getting into more specific from the generic, okay? Because at the beginning we showed the bigger picture. Now we are going to a little bit in more specific format. Now in this class, whatever the instruction you will see the instruction in this format. Remember, in C++, you have plenty of instructions, right? You don't have limit of how long the instruction can be, because let's say you can write A equals to B plus C plus D plus E, no matter how long you want. You can write all sort of mathematical expression in the way you want. But here we have some restrictions, okay? We cannot write anything beyond that restriction, okay? Now, oops, I accidentally pressed something. Let's go back. Okay, now here. Now, what is actually an instruction? Again, we are now in very specific point. All the instructions you see here, those are written, designed by Motorola, but every microprocessor has some set of instructions. That means it understands only those instructions, nothing else. That means, for example, if I have a microprocessor, even whatever you have in front of you, that has a list of instructions, like 50 instructions or 100 instructions. It basically understands only that set, nothing else. Do you see what I'm saying? It only understands that, nothing else. Now, the Motorola microprocessor that we'll be dealing in the lab, we'll be using in this class, has a set of instructions. That's also in pause. Okay, I'll get back to that. Now, each instruction in this class, in Motorola microprocessor, will have two parts. Do you see there? First part is called opcode. What is opcode here? See? LDAA, right? It is not LDAA for, meaning there are plenty of other opcodes. This is one of those, okay? Second part, that will be a number kind of thing, okay? That is called operand. So that means what? Each instruction will have two parts. opcode and operand. You see what I'm saying? First part, it will be some sort of letters like this one, LDAA or something else like this. We'll see the list. Second part, it will be a number kind of thing. And you see, even in front of the number, there are some additional symbols, right? See, there is a hash symbol, or I would say pound symbol. You know, is pound, right? But in computer language, we call it hash. But you know this. Probably pound is more familiar because we all go by the cell phone or phone pad, but that's, you know, that's hash. And there is a dollar sign, right? We don't understand what that means, but we'll understand it soon or over the time. But again, instruction has two parts, right? Now, again, every instruction, whatever the two part you have, that also has two other format, meaning that means whatever the code you have, like opcode, that opcode has a specific meaning to the compiler, meaning to the microprocessor, okay? And that is written by code. Like for an example, LDA means 86 for an example, to make it simple, okay? And the operand is 02, still that is 02. So at the end of the day, microprocessor just read those numbers. Now, what is 86 and 02 here? Again, I think I forgot to mention, whenever we write any number in this class, in the slide or in the board, anywhere, that's in hex. No matter what number, unless I mention is something else, that is hex. Now that means what? 8602, that is a hex number. We'll not mention every time, but that is by default hex. Anything we just write, hex, okay? Unless I mention that this is binary or this is decimal, that's hex. Any number you see except your student ID or the quiz number. Okay. Now again, at the very beginning of this class, let's say we don't understand anything at this point. We don't have any idea what is instruction except, you know, opcode or like operand. We'll first try to understand this. Given any instruction, it has a mode. We actually don't understand the purpose of the mode, but we will be able to identify the mode just by looking at the instruction, not even by understanding anything. Okay? We'll try to understand the mode. We'll try to not understand, I would say, we'll try to identify the mode. Okay? We have 6 different types of mode. We don't even know the purpose, but soon we'll know the purpose. Okay? Now let's first try to identify it. What are the modes? Immediate, direct, extended, inherent, right? And the last 2 are relative and indexed. But in this class, just for today, just for this lecture, we'll be just exploring the first 4. That's why I just blurred the last 2. So in total we have 6 modes, but in the somewhere in the probably in the later we'll talk about the other 2. But today we'll just talk about the first 4 modes: immediate, direct, extended, inherent. Now what is our job is, given any instruction, even if we don't understand it, just looking at the instruction, can we tell what is the mode? It may be immediate, it may be direct, may be extended, may be inherent. How do I know it? Let me give you some clue. Any instruction, whatever the opcode is, all you need to look at is the operand. You know, the second part is the operand, right? Second part, okay? If that starts with a pound sign, that's it. It's immediate. So easy, right? Is the operand? Yeah. You know, the operand is the second part, right? If this part, I'm talking about this part. If this part starts with a pound sign, that's immediate. Very simple, right? If that starts with a pound sign, immediate. Now, how about direct? No pound sign in operand, okay? But can you read the data? What is this data? Hex, right? If it is in hex or whatever, if it is 1 byte or less, now how do I know it is 1 byte? What is 1 byte? 1 byte means what? 8 bit, right? Okay? How do I know whether it is 1 byte or not? In hex, remember, just try to recall, every single hex digit means what? 4 bit, right? in binary? Can you recall, remember? Digital circuit class? Every single hex digit means 4-bit in binary. Now how many digits you have in here in hex? 2 digit, right? A2, that means it's 8-bit, right? That's mean 1 byte. You see what I'm saying? Now remember, just for the operand, don't forget this. Meaning, you know, over the time we'll know it, so again, practice again and again. If there is a $sign, meaning the data starts with a $sign, there is a $sign, that means whatever the number we are writing, that is hex. If there is a percentage sign like this, do you see there is a percentage sign? Then whatever we are writing, that is binary. If there is no $sign, no percentage sign, that is decimal. I tried to give you 3 examples, one from decimal, one from binary, one from hex. Meaning, how do you know what number it is? Because if I just write 162, it might be binary, it might be hex, right? I'm saying it might be decimal, it might be hex, right? So, the only way you know is if there is a $sign, that is hex. Percentage sign, binary. No $sign, no percentage sign, decimal, right? Now, can we tell, is this a 1 byte or not? 1 byte means what? 8-bit, right? If it is a hex, just look for 2 digit. I'm saying A2, right? This is hex. If I have 1A9, that's not in 1 byte. That's more than 1 byte, right? Okay. Now, if it is a binary, what is 1 byte? It must be 8-bit or less. If it is more than 8-bit, it's not 1 byte, right? It's more than 1 byte. Now, if it is decimal, how can I tell it's 1 byte? It must be 255 or less, right? 255. Because if you have anything more than 255, you cannot write it in 1 byte, right? Remember, what is 255? All 1, right? 8 ones. No, 256 is 1 following 80. Yeah. So, any number, decimal number, if it is 255 or less, I'm talking about the unsigned number, okay? In general, I talk about the unsigned, otherwise I mention. If it is 8-bit or less, that's 1 byte, right? Meaning, in decimal, if it is 255 or less, that's 1 byte. That's how I know it's 1 byte. Now, addressing mode again. If the operand is 1 byte and there is no pound sign, remember, pound sign is something else, right? If there is pound sign, we know that is immediate. We don't even look at for 1 byte, 2 byte. That's immediate. If there is no pound sign and the data is 1 byte, that's what? Direct, right? Addressing mode. Now next one, extended. No pound sign, but the data is more than 1 byte, meaning 2 byte. Look at this one, the first one. That's what? Hex, right? How many byte? It's obviously more than 1 byte, right? It's 2 byte, right? Because every digit is what? Every hex digit is what? 4 bit, right? So there are 4 hex digits. That means what? 16 bit. It's 2 byte, right? It's even more than 8 bit in binary. Obviously 2 byte, right? And this number is much larger than what? 255, right? So that's 2 byte. So that's 2 byte. Now the last addressing mode for today is inherent. Inherent is probably the easiest one, because in the inherent we don't have any operand. That's so simple. It's just no operand, okay? It's just the opcode. No operand. There is no operand in the inherent instructions. Okay, now let's check here. Okay, before I go here, let me give a pause here. Let me give a pause here, and I'll show something. Just to let me give a pause, okay? Now, this is the set of instructions for the Motorola microprocessor we'll be using. This is a 6-page instruction list, okay? We probably will not understand most of it right now, but in the very left side, if you look at the very left side, these are the list of instructions, meaning these are actually the opcode, okay? And we have 6 pages here. Don't print it right now. I'll give you a compact printout, like both page, 6 page. If you want, you can print, but I'll give you a compact one. You can use it from here, but so whatever the instruction we have here, our microprocessor only will understand anything from here, nothing more than this. Okay? And over the time, we'll pretty much understand the whole part of this instruction set. And that's actually the purpose of this class, to understand it and to apply it. Okay? Let's see. So whatever you see here in the slide, that's from here. Okay? Let's see. Now, we have an instruction here. In the quiz one, we'll do this sort of question. We'll give you an instruction like this, and we'll ask, what is the mode for this instruction? Can anyone tell what is the mode? That's immediate, right? Why? There is a pound sign in the operand, right? Remember, if you have a pound sign, that's probably the easiest. Immediate. How about this one? Direct, right? Because no pound sign, first of all. And can you tell what is the data? Is it decimal, is it hex, or is it binary? 35. Decimal, because there is no pound sign, no dollar sign, right? So that's direct, right? How about this one? That's inherent. That's probably easiest because you don't have, so that's inherent, right? How about this one? Extended, right? Why extended? No pound sign, so it's not immediate. It's not inherent, obviously, right? But look at the data. That's in hex, right? Because there is a dollar sign. It's more than a byte, right? So that's extended. So the answer is extended. How about this one? Extended, right? Because it's 255 is the largest decimal number, is 256, which is extended. And there is no pound sign. There is, so that's not immediate. So that's extended. Okay, so that's extended. How about this one? Direct. Okay, now let's see this. Surprisingly, this is not direct, this is extended. Why is this? That's out of the definition, right? This should be direct, right? No question about that. But remember, as I said, we always go by the set of instruction, right? Remember the 6 page I just have? Now let's go to the instruction. Let me show you something here, okay? So this is the instruction, and all the instructions you have seen is from this list. What is the instruction again? Remember, it's NEG, right? Let's find NEG from this list. Now, do you see that? Was it just NEG, right? Okay. Now, this was the NEG, right? Do you see it? Do you see I'm highlighting NEG? Now, whenever I have an instruction, I have list here. These are the possible addressing mode of the instruction. Okay? Remember, the sum instruction does not have some specific mode. Look at this instruction. It tells that it has extended mode. It has indexed mode. We did not talk about the indexed mode in this class so far, right? But look at this. It does not have any direct mode. Do you see it? That means whenever you will have the answer for any question, look at the set of instruction. If it does not have direct, it is automatically extended. So you always have to check back here. We know that there are some, if this is that, if we know this, but you always have to check here. In some cases, in some instructions, you don't have direct move. So that's why you always have to check the column 4. Okay? If you don't see direct, that means that is extended. These are exceptions. I tried to list one exception just to make sure you know that there are some exceptions, okay? So whenever you know, oh, this is direct, let's check. You will check the column 4, you will see there is no direct mode, that will be extended. Okay? Now, at this point, you are actually ready for your first quiz. Any question? We might have question when you will be there, but in the quiz 1, We are ready for quiz 1 right now. If you're done with your quiz 0A and 0B, at least with 65%, you can start trying the quiz 1. In the quiz 1, you'll pretty much see similar questions. It's all multiple choice. So you'll be given an instruction. All you have to tell is what is the instruction mode out of 4 in the list. Okay? It's very easy. Let's try it. And this is the first thing we need to understand to start anything after this point. That's why we will be going in sequence. If you understand this, you probably will understand the next part, right? Let's try the quiz and make sure that we are done with this quiz before we come back next time. Okay? And also make sure you always have to finish the quiz 0 and 0B. And even if you have finished it, not with 100%, later on, try it during weekend or whenever you get a chance to get 100% in every single thing. Because remember, we have a 30% coming from the quizzes and sample test. To get that 30 out of 30, you have to have 100% in every single quiz and every single sample test. But you can try it again and again. That's the good news. Okay? Let me stop this presentation so that you can go to the quiz section and you can try the quiz 1.